engineers determine each panel's exact dimensions, shape, and reinforcement needs based on the building's specific structural requirements. Engineers also consider factors like load-bearing capacity, insulation needs, and aesthetic finish to ensure the panels meet both functional and architectural standards. Once the designs are finalized, forms, typically wooden or metal molds, are crafted on-site to shape the panels accurately. These forms are meticulously constructed to match the panel designs, ensuring high precision for the finished product. This step is critical because accurate molds ensure proper alignment and fit when the panels are later erected. Steel reinforcement bars, rebar, are then strategically positioned within the forms to provide the panels with the necessary tensile strength and resistance against cracking. The placement of the rebar follows strict engineering guidelines to ensure that the panels will effectively withstand the stresses and loads they will encounter over time. After reinforcing the forms, high-strength concrete is poured in, carefully filling the molds. To ensure that the concrete is dense and free of air pockets, which can weaken the structure, workers vibrate the concrete during pouring. This step is crucial for achieving a solid, durable structure that will maintain its integrity over years of use. The panels are then left to cure, typically for a period ranging from several days to a few weeks. This curing phase allows the concrete to achieve the necessary strength and stability, ensuring the panels are rigid enough for lifting and resistant to the environmental conditions they'll face once in position. Once the curing process is complete, each panel is carefully raised and secured in place, creating a strong, weather-resistant exterior for the building. Once the concrete has cured to the required strength, the precast panels are carefully lifted into their vertical positions using cranes. This phase requires precise coordination and meticulous planning to ensure each panel is correctly aligned and securely placed. Specialized lifting clutches are attached to cast-in inserts on the panel, and the crane cables are tensioned once all clutches are connected. A thorough inspection ensures that each connection is secure before lifting begins. A spreader bar is often used to adjust rigging configurations for various panel sizes, enhancing stability and control during lifting. Using hand signals, workers direct the crane as it moves each panel into place. Once aligned with the foundation, the panel is positioned with shims inserted to make fine height adjustments as needed. Temporary braces are then attached to hold each panel firmly during construction of the remaining building shell. Once the braces are secure, tension on the lifting cables is gradually released and the rigging is disconnected, allowing the crane to reposition for the next panel. This process is repeated systematically until all panels are erected. Tilt-up construction, once reserved mainly for large warehouses, has evolved to become a preferred building method for developers, designers, and contractors across various project types. The process is not only efficient but offers several key advantages. Key advantages of tilt-up construction. Speed. Tilt-up construction is highly time efficient. Once the concrete panels have cured, walls can be erected in a fraction of the time required for traditional construction methods, accelerating overall project timelines and reducing labor costs. Cost effectiveness. By minimizing the need for on-site labor and materials, tilt-up construction can be more economical than traditional approaches. The panels, often fabricated off-site, allow for tight control over production schedules and costs. Durability. Concrete's inherent strength and resilience make it ideal for long-lasting, low-maintenance structures. Tilt-up buildings offer superior resistance to environmental factors, ensuring longevity even under harsh conditions. Energy efficiency. The thick concrete walls, characteristic tilt-up construction, provide substantial thermal mass, offering natural insulation. This helps maintain a comfortable indoor climate, reducing energy consumption for heating and cooling. Design flexibility. Tilt-up construction is adaptable to a wide range of architectural designs from small warehouses to expansive industrial complexes. Customization options allow for panel modifications, accommodating diverse project specifications and aesthetic goals. Tilt-up construction has proven itself as a versatile, reliable, and cost-effective method for modern building. Its combination of speed, durability, energy efficiency, and flexibility continues to drive its popularity among developers and builders looking for sustainable and scalable construction solutions. The construction of the Northman Causeway employs a pioneering method of precast segmental balanced cantilever construction, showcasing several key advantages of this approach. To construct the ramps and bridge sections, two different metals are used in combination with specialized equipment, such as Cravid crane for lifting segments and a launching girder to support the placement of segments along the bridge spans. Additionally, a shoring tower, elevated above ground level, provides support during the construction sequence, which includes piling, pile caps, piers, bearings, and precast segments. The foundation of the causeway consists of cast-in-place concrete piles installed by drilling shafts to a precise depth and diameter determined by engineering specifications. Once drilled, a reinforced steel cage is lowered into each shaft, which is then filled with concrete. Multiple piles form a pile group, which is capped by a pile cap that serves as a stable foundation. This pile cap distributes the weight and loads from the bridge structure above, transferring them to the underlying piles. Each pile cap supports one or more reinforced concrete piers, which are essential to bear the load of the bridge superstructure. Before the precast segments are mounted, bearings are secured on top of each pier. These bearings accommodate thermal expansion and contraction, and they also allow for small rotational and translational movements, absorbing stresses to ensure structural integrity under dynamic loads. Bearings are custom designed for the specific requirements of the bridge. Segmental bridge construction involves assembling small, precast concrete segments individually rather than constructing the bridge in large sections. These segments are cast on the ground in a dedicated precast yard using the short line casting method. In this process, each segment is cast in a stationary steel mold adjacent to the previously hardened segment. The fresh segment, known as the day-old segment, is shifted after 10 hours to align precisely with the previous segment, ensuring that all joints match perfectly during final assembly. In the final structure, segments are transferred to a storage area, then lifted into position during bridge erection. At each pier, adjoining segments are joined by coating their surfaces with epoxy. Temporary post-tensioning bars secure each segment to the cantilever structure, with post-tensioning tendons added as more segments are erected to achieve a balanced cantilever. As the segments are placed symmetrically, a link slab is cast at mid-span to join cantilevers, forming a complete span. Adjacent cantilevers are connected at closure joints, forming a continuous bridge structure. This method, especially when using a launching girder, minimizes traffic disruption in high-density areas, such as busy junctions, by reducing the need for on-site interference. The short-line casting method in balanced cantilever construction allows for precise alignment and error detection, facilitating adjustments and ensuring the durability of the bridge. This method also accelerates construction and reduces costs, providing a reliable and efficient solution. Traffic management for this project is organized in 9 stages, starting from stage TM1 and concluding with the final endline stage. This phased approach optimizes both construction progress and traffic flow management. The prefabricated segmental method, PSM, offers distinct advantages in large-scale bridge construction, particularly in terms of time efficiency, quality control, and safety management. Hyundai Engineering and Construction leads the project alongside 9 partner companies, working on an ambitious schedule that spans 44 months, from December 28, 2009 to August 27, 2013, with an estimated budget of approximately $2.6 billion USD. The total construction length covers 9.6 kilometers, incorporating complex elements such as a 285-meter main bridge span, various segments of 9,310.5 meters, PSM with 3-span steel arches, and additional specialized segments like Extra DOS and FS-MSS using the Gassel construction method. Specifically, the PSM design includes 218 spans of 35 meters and 14 spans of 30 meters, totaling 8,150 meters. The PSM on-site construction employs a pre-stressed concrete PC box girder system, leveraging advanced prefabrication techniques. The primary girders for the Hankyung River span are manufactured off-site at a dedicated PC production center, utilizing precision molds. These girders are then transported to a temporary assembly point for final placement, a process known as the go-to launch technique. This approach enhances stability in the work environment, ensures consistent quality through automated quality control, and strengthens safety management. The construction sequence for the PSM method is carefully structured. First, the PSC box girders are produced at the PSM production center. Diaphragm steel meshes are pre-assembled at both ends of the girder, then lifted and positioned with a 10-ton gantry crane. Floor reinforcements and central wall steel bars are installed. Bulkheads are positioned at both ends, and internal steel tracks are added to reinforce structural integrity. Using dual gantry cranes, inner components are placed and pictorial rebar is set up. Once the rebar assembly is complete, a chiffon gantry crane installs deflection prevention bars to maintain structural alignment before moving to the casting phase. The assembled steel net is transferred to the casting yard where a 9-part mold is set up. Following mold setup, a 70-ton gantry crane dismantles the rebar deflection prevention bar, ensuring the segment is stable and prepared for casting. This streamlined prefabrication focused process not only accelerates the timeline, but also enhances the overall quality and safety of the construction. After installing the thrust head for pretensioning, the initial reduction in dimensions is anticipated. Once the preparatory work is complete, approximately 350 feet of concrete is poured, facilitated by 2 flushing balls to ensure even distribution. Following the concrete placement, a curing period of 12 hours is strictly observed to enhance strength and stability. Afterward, a compressive strength test is conducted, and if the concrete achieves a threshold strength of 30 megatonnes, a curing membrane is applied to seal in moisture and optimize the curing process. When curing concludes, an InnoMold system is employed to withdraw the molds. Then, using 2 70-ton gantry cranes and a 20-ton winch, the concrete structure is moved to its final location without disturbing the inner formwork. 2 500-ton gantry cranes are then used to load a third tire trolley, which is positioned near the third section of the bridge. This trolley carries the PSC pre-stressed concrete box girder to its designated erection point. Once aligned, the structure enters the initial positioning phase where it is elevated. After securely fastening the PSC box girder to the trolley, the girder is transported to a temporary staging area. Here, it is gradually lowered onto the camper rail, which has been pre-installed on top of the coping for added support. The Essel Brunch system initiates the process of self-launching by first strengthening the overall assembly. The lifting trolleys are then maneuvered to the rear of the launching girder. Once in position, a wire is connected from the trolley to the PSC box girder for stabilization. The front legs are then detached, folded, and moved to the thrust area, enabling further assembly. With the front leg repositioned, the lower slender section is raised, and the trusty ego wheel is placed on the rail. The rear anchor wire, previously connected to the axle, is released, allowing the launching lifter to advance forward incrementally. Upon completion of this phase, the rear anchor is once again secured. The next step involves securing the PSC box girder as the structure is incrementally advanced. The front rack, equipped with a steel rod, is adjusted and secured in place. After completing the front lag EcoPing installation, the next PSC box girder is positioned for installation. The rear anchor wire is then attached, and the lifting trolley is moved to the Type 2 PSC box girder location. The operational process continues with precise adjustments and alignments for each subsequent PSC box girder, ensuring structural continuity and stability throughout the project.